Okay, so I've got a bit of an update on where we are with one of the sub-projects within the FD.io, the continuous system integration and testing and performance benchmarking. So some of the material here, especially the high-level marketing blurb, is the same, but there is a lot of new data, hopefully of use. So my name is Maciek Konstantynowicz, and I'm a project lead for FD.io SysIt, and I really represent here the work done by the community. And this doesn't work. Click works. Okay. There is quite a lot of data here, again, hopefully of use. This data is generated by the labs that we operate within the LFN. But your mileage may vary depending on what hardware and software stack you use. We do our best to document everything that we do and how things are set up. So, and we claim a good reproducibility. But again, your mileage may vary when you try to replicate the tests on slightly different hardware or software stack. And there are some trademarks and branding have been asked to put this disclaimer in. So, how does, from the use case testing and benchmarking perspective, how do we see VPP fitting into this new world of cloud-native applications? We have NF and SDN, which are the trends that started in telco world quite a while back, and they are now being married by the cloud, underpinned by cloud-native designs. But the core, really, of the technology that we strongly believe in is the open source platforms that underpin the internet trends across those dimensions. I've put this slide together last year about the Moore's Law. And in literature and everywhere we hear that Moore's Law is pretty much dead. And Intel and others are finding it hard to follow the Moore's Law. It's getting more and more expensive. But how does this apply, and if it does apply, to our space, to our software networking space? And I obviously have lots of opinions, and as does everybody else. But the data shows us that it is still rambling on. And with the new generations of processors, we're getting higher and higher speeds, mainly because those vendors are paying more attention to I/O and networking, which is all good news. And if you're wondering what this thing is, I had the pleasure to touch it. It's the pre-1900 hole puncher. It's a 7-bit, and it implements whoever built it, it implements the binary logic and Boolean logic and binary. So when we benchmark, we clearly need to pay attention to how computers process packets, and we try to share this knowledge as much as we can with the development community and user community. You need to be aware of the physics and the hardware to be able to make efficient use of it. And whether these are shared resources, processor CPU cores, memory bandwidth, I/O bandwidth, inter-socket. The most important we're paying attention to is the packet processing piece, CPU cores, but there's a lot of stuff to do with memory and I/O handling. Now the Moore's Law rambling on piece is a slide that I again presented at CUCO in Seattle, is that with moving from one generation to another on Intels, from Broadwells to Skylakes, we actually noticed significant performance gain, and we keep seeing that gain even for the new code and the new test cases. And this is due to the various microarchitecture improvements that result in the performance gain. If you have any more detailed questions about technologies listed, I have a number of references. I'm also available after the talk to discuss them in detail. So this is the 5 dimensions that we believe any new modern software data plane should aspire to and should meet the requirements. Software comes first, so any retrofitted technology will always have to compromise on the efficient use of software-hardware interface. It needs to be fast, clearly, covering both the east-west and the north-south traffic. And we have this, well, I guess thanks to the cloud and containers, a massive explosion of east-west traffic. So focusing on that is clearly paramount. And then, being truly extensible and having a predictable performance, even in the box full high service density scenarios, is clearly one of the table stakes. And in order to achieve all of those 4, any modern software data plane should count and provide a telemetry of not only the traffic that flows through it, but also resource usage. And the claim we put in here that VPP does meet all of those challenges, and a number of them we're proving in CICIT, what we refer to as open source benchmarking labs. These are our principles. We like to know the limits if you don't, and discover where things break. We want to treat the systems as black boxes, but also understand what happens when they break, and if there are any ways to improve them as a white box, and share it with the community. So that was it from the sort of overview. I'm now going to go into a bit more detail, some small print, and quite a lot of data, hopefully without overload. So what do we do in CICIT? We do continuous testing, and we generate those reports per release. The latest one is 1904 that went out about 2 weeks ago, or 2.5 weeks ago, and we test various processor platforms: Intel Xeon, Atom, and ARM. Intel Xeon's been in the labs since its inception in 2016. Atoms are up and running, although we still have issues generating the full report data from the devices in the labs due to various logistical issues. But we are pretty much 95% there. So next release, all the data will be produced from those testbeds, and a similar thing applies to ARM. We test various packet paths, including containers and VM paths. We do a lot of test cases, we do a lot of measurements, but we also focus on repeatability and comparing apples to apples, and also release to release. These are the emails that we sent on a per report basis, just with highlights on what the reports contain. And I'm going to focus on the next slide, some highlights on the performance front. So how do things look in 1904? Well, to get a full picture, you need to read the report. We've been asked to do our best and provide some sort of a technical marketing summary on what happens and in the release, and this slide deck is the first attempt to do so. Unfortunately, we don't have really much resource or time to write a glossy collateral, but we welcome any help and all help in that area. So the 2 charts are copy paste from this page, and I have another specific page to prove that, showing the performance of the IPv4 forwarding and L2 forwarding on the Baremetal NIC to NIC. You can see here the baseline forwarding, and with some at some capacity of the IPv4 FIP, 20,200K and 2,000,000/32 prefixes. And the data is listed as shown, so it scales from 15 to 18 million PPS per 1 physical core. And this is on the 3-node Skylake and Fortville X710s. What is interesting to see that these are the non-drop rate throughput data, which means that not a single packet is lost. Okay, we run those tests 10 times, different times of day, different times of the week, and this statistical data show the spread of the results. As you can see, for the median here at 15.68, the min is 61 and the max is 76. So it's only a few tenths of kpps difference between the runs for the zero packet loss. And that's basically shows a great repeatability. If we look to L2, speed is from 12 to 27 Mbps. Although 27 is really the current max of our T-Rex, as we have some issues with DPDK compatibility. But these are the shortest, the fastest path, L2 patch and L2 cross connect, and they're just indicative of what the software I/O path can do. But again, for L2 bridging, baseline at 18 million, and with 1 million max at 11 million, it is still state-of-the-art and industry best. We believe the spread goes a bit wider for some certain cases, but it is still within, in this case, about 1 Mbps. So how do the releases compare? So there's a question from Jim.
Clock speed on the Skylake core you're using?
Sorry?
Clock speed on the Skylake core you're using?
2.5 gigs, so it's 8180. And that's the right question to ask. I will add that to the thing. Core frequency clearly matters. We run it at the base frequency for all tests, as you can imagine. No turbo boost. You can calculate the clock cycles. Improvements from release to release. This is the NDR data, again, zero packet loss. Certain paths, VM specifically, and VM vhost and AVF improved quite a bit, 10 to 20%. This list is generated for all the tests that run, and with the descending order, so you can see which paths improved most. And the dedicated links are here. And that's the comparison between the Skylake and Haswell / Broadwell. We still see a big numbers as per the sort of Moore's law rambling on. So that was it for data. Now the new stuff we've done in this release is we've been working for some time to address some of the challenges we're facing with specifically executing the tests and having a limited physical resource. So we started to innovate and get smarter with the way we test. The results are 3 new methodologies that we have developed. The first one is MLRsearch, which is an improved and more efficient binary search of sorts, where we can search for multiple rates in one walk, and be smart with the timing. And we're standardizing this in IETF to augment RFC 2544. Second one is maximum receive rate, which we're using for a very fast spot tests and evaluations. And here we actually don't care about the packet loss. So in this case, in SysIT, we test against the zero packet loss, NDR, and PDR, which with some packet loss that's not greater than non-zero. Here we don't care about the loss. And what we're using MLR for is for trending. So we run tests daily for the designated packet paths, and we basically watch the MRR result and used some machine algorithms to detect the progressions, regressions, and notify developers. So in this case, you see AVF improvement that happened around the 3rd of March, and then again around here. When you click on those dots, you get a lot of info to correlate the patch and so on. The thing that we starting to be most proud of from the innovation perspective is we developed something we refer to as automated soak testing. So, we do know what soak testing is. We want to know how the system behaves long term, throughput, latency, any resource leakage. But to do it properly, ideally you need a human to sit and to watch it and or check it after a while and then understand what happened before. But human labor is not cheap. So throwing people at the problem clearly doesn't work. So what we did, we developed an algorithm we refer to as MLRsearch, probabilistic loss ratio search, which replaces the human. And it's using some maths, some hardcore probabilistic maths, and the result is really heuristics that emulate the human behavior, basically an operator sitting at the thing and with a knob and trying to find a rate that is compliant with the criteria. In this case, the criteria we gave was 10 to minus 7 packets per second, which is the ITU named for a long-term zero loss. And as you can see here, applied to the VPPL2 patch, the algorithm adjusts over the 2 hours of the test and ends up with a critical region, as we call it, precision of 25 packets per second. And the longer you specify the time, you can run it for a few hours, for a day, for a week, for a month, for a year. And the algo will be basically monitoring the system behavior and adjusting to the 10 to minus 7 in this case. Applying this to another case, vhost with a lot of VM interrupts and memory interface, we're getting a lower precision, still good, 20 kbps. And this release is the first one where we have a high confidence that the algorithm works. And you will see on the next table, it's the data is matching what we expect. Now, maybe this looks a bit futuristic, and I don't know who is looking at the 25 bps precision on the software NFVs. Software NFVs do not tend to have a good reputation when it comes to deterministic behavior. But as we can see, certain paths can be explored in the sort of precision range. The thing here is that we do not prescribe the precision. The only thing that we prescribe is the packet loss ratio 10 to minus 7. So we run this through a set of paths with VPP, including some container and MEMIF and VM vhost paths. And we compared the NDR throughput discovered with this MLRsearch algo and the soak throughput. And the results are matching. There are some discrepancies on IPv6 base, and we expect this is to do with LLC games, but over time. But it's overall we are very happy with the results, and I think we can now call it a production ready for experimental use. And we also, I think I had a note on previous slide. We're also looking to standardize this in ITF. Although, to be honest, BMWG Group is hesitant because the maths involved are quite heavy, but I'm sure we're going to get there. So now another thing we did, and we sort of give a taste of this at KubeCon Seattle, is the result of a collaboration with CNC FCI team and as part of the CNF testbed, is the attacking another problem, which is verifying the behavior of the system where you have a lot of NFs in a system. And how do you benchmark a system like that, right? VPP standalone is cool, as we're proving, it's deterministic. How do you approach when it's more of them or there are other applications? And here we We also took a sort of semi-standardization approach, and we put a draft together where we're looking to come up with a methodology that allows one to, in a universal manner, benchmark a server full of NF services. So we have identified some direct factors and some indirect factors. Direct factors are, what NF code, how it is configured, what are the virtual topologies, what are the packet traffic profiles. And indirect factors are how what are the technologies that are used, shared technologies like virtualization and host networking that are used to underpin the services. Okay, I'm gonna skip that due to time. But we basically identify the NFV service, we separate virtualization technology, we separate the host networking, and in our testing, we're actually comparing virtualization technology, vhost VM, and Mammoth container, and vSwitch as a 2 layers, and we manage some core resources, and we're looking to do some tricks with LLC going forward. So how do we abstract the service? We define how these network devices are interconnected, how they are configured, and how are the packets flowing through this sort of topology and configuration. And with that in mind, we defined 3 scenarios. VNF service chains with snake forwarding, as you see on the slide. So packets coming in on the virtual switch, and then go snake forwarding over the VNFs. Same, but with containers. And the third one is because with containers, we have this horizontal Mammoth interface. We have this pipeline forwarding that is loading the vSwitch less. So these are the three topologies that we benchmarked fully in 1904. We created this service matrix, density matrix, with rows listing number of services and columns listing number of NFs per service. We applied some core mapping magic, which we're also looking to standardize from the approach and naming perspective in ITF. So we're taking vSwitch with 1 core, 2 core, 4 core, and NFs with half core, 1 core, 2 core. And we're applying different core resources depending whether the hyperthreading or SMT is enabled or disabled. Of course, number of total services is dependent on the core usage. So in SysIT, we test the gray ones. We can't test the red ones because of running out of core resources. So anyway, these are all the boring things. And now what we tested, and the results are here. So we took the virtual service chains, and we tested M of them, so up to 10, with up to 10 VNFs. And the configurations were VPP running 1904 with L2 switching as a vSwitch, and IPv4 routing as a VNF with different resources associations. vSwitch 1 core, 2 core, 4 core, and NFs 1 core, half core. We didn't really know what to expect, so the results were actually interesting. Now, the second one is the same for CNF service chains, and the last one is for pipelines. So does anybody know, if your brains are still working and you're following, on which one of those is expected to be the fastest? Bottom. And second fastest? Giles, you know too much. So these are the results. If you're interested in a sort of top-level message, the CSP, the pipelines, are up to 5 times faster than CSC. We are measuring mainly the forwarding performance of the vSwitch. So vSwitch is a containing factor, and this is the least using vSwitch. So this is clearly expected. C is up to 30% faster than VSC. Containers are a bit lighter weight, but here it's mainly to do with the I/O packet interface optimization, so 30%. And VSC is the slower, but the data is as shown here. So the blue bars are for a single NF per chain. So that's clearly the fastest for all cases. About 4.5 for VSCs and over 5 million PPS for CSCs and over 5 for CSPs and so on. Now what is interesting, yeah. Mammoth. Pure Mammoth. We have VBP is the CNF, so it's VBP IPv4 routing as running in a container, talking directly to each other.
So you're not doing Libromif applications?
No, yet, not yet. Okay. Now this is with the NFs running on one core. Funnily enough, that if we put the data plane worker threads on half of the core, so on a single hyperthread, the results are staying pretty much the same. For CNFs, they're slightly lower for VNFs, which means we can pack more services on the socket. Okay, so what we're doing next? We've done the work with, in terms of this NF service density, we've done the work with homogeneous NF apps, VBP-LA3 forwarder, and configurations. We're looking to do different configurations and looking at heterogeneous NFs. Now, this is a bit out of scope for FD.io assisted per se, but we're collaborating with CNF testbed, and Lucina is here representing the team. We're basically looking for inputs on high-performance NF service use cases and the requirements. We believe that this work will underpin any such use cases as they come along. So IPv4, IPsec, NAT4 firewall, stateful, and so on. And this is just to call out the old slide of mine, the material we put in 2017, showcasing the Intel Xeon Skylakes and 1 terabit per server. And maybe a quick recap on Mammoth. A friend of mine asked me to remind the community that Mammoth is still there and is ready to be used. So in case you're not familiar with Mammoth, Mammoth is the shared memory interface that is that can be used to a packet interface to connect processes together or containers in the user mode, and it's optimized, as I will show on the next slide. In the container space, it lends itself very well to connect containers together, as I have presented earlier. So it's safe and secure, zero memory copy on slave mode, on slave side, and it's optimized performance, not only for packets per second, but really how many clocks are used per packet, and also instructions per cycle on Xeons, Atoms, and ARMs. And there is a Mammoth library available, libmammoth, and there is a link to the docs on that. Just a repeat of, we're driving some standardization work with ITF and ETSI. And I think this concludes my slide with the usual wrapper of VPP is the one. Okay, thank you.